So a very warm welcome to this intuitive introduction to RAG. This is a 3-evening course. It will be today evening, Wednesday, tomorrow evening, and next Wednesday. We are going to cover 2 topics in this course, AI search and RAG. The 2 are interrelated because AI search is a part of RAG, and the reason I'm putting it separately is because we are actually going to spend some time on AI search, not just skip it and go straight to building RAG code. The way we'll do our sessions is we will talk and explain concepts for about an hour, and then I'll walk you through some labs, some code for the next hour. Because it's the first day, I will help you set up your environment. I'll show you a modern way to set up your AI development environment very quickly. In just 3-4 commands, it would be set up. But we'll do that in the lab part, which will be the second half of today. So with that introduction, I should also like to mention once again that we are going to start a pretty exhaustive RAG and AI search bootcamp, which is starting on February the 20th. It's a 4-month bootcamp that is on Thursday evenings and Tuesday evenings. Very much like our paper readings, they start at 7 p.m. and they're 3 hours every day on Thursdays and Tuesdays. So in that particular course, we do every aspect of RAG very exhaustively. So in this particular course, to the extent that it is an intuitive introduction to RAG, I would request that if you have a very detailed and technical question, ask it, but I might park it because the audience that would be here are people who are probably trying to get a first-time introduction to RAG systems. So for their sake and to help them gain from it, let's keep very technical questions for hopefully for the bootcamp. With that introduction and those statements there, I would now like to get started with the main topic itself. So I tend to write and talk in an interactive manner. I don't usually have prepared slide decks. So I'll explain what RAG is, what AI search is, and from there onwards, we'll do some labs, some code. The code that we show you, we will post it to the course portal. I would strongly encourage you to register yourself to the course portal, and there you'll see a course, Intuitive Introduction to RAG and AI Search, the 3-day course that will give you access to a lot of resources. So on the chat, you'll see, or maybe I can screen share after a little bit. For the time being, let my teaching assistants, they will put it on the Zoom chat a few times so that you can visit that and register for the free course also. If you register for the free course, what you get is access to any code that I show today, tomorrow, or the day, or next Wednesday. All of that code will be there for you to download and play with. That's the only advantage you get. And you'll also get a quiz and so forth to help you strengthen your knowledge. Okay, so with those preliminaries out of the way, let us go to the topic of search. See, the search, or what people call the information retrieval, has been a subject, has been an industry for a very, very long time, for decades. There are broadly 2 ways that you can search for things. One is decades old, and one is quite contemporary that has evolved within the last decade. I'm going to first talk about the former way, which is called keyword search or sparse search. So let me put the words there. Search, keyword search. It is also called BM25 search, or it's also called sometimes just TF-IDF based search. But generally, these words we will consider as broadly synonymous. Most of the modern search engines, traditional search engines like Solr, Lucene, Elasticsearch, OpenSearch, they are based on BM25. To understand what is the value of AI search, let us first get a very simplified understanding of traditional search or keyword search. The keyword search leverages something called fundamentally called inverted index. So as I explain this, I will deliberately eschew all the complexities of creating a production grade a search engine using keyword search, because there is a lot that goes into it. The topic has evolved quite a bit, and most of you must be using one of these search engines in your workplace, and you may not even know that you're using it in the background. And they have been industry workhorses for a long time. So the picture that I'll give you is conceptual and a bit oversimplified, because we have ultimately 3 evenings to go through all of this. So think of it this way. Suppose I have a document. One document says the cow jumped over the moon, right? And today, the other document, D1, has this content. D2 has a content. The cows are happily grazing in the meadow. And let's say D3 has the text, today is a full moon night. And fourth one is, let us drive over to the meadow. And I'll imagine that the world is made up of just 4 documents. Here is what keyword search in simplified form do. First, what they do is they go through the documents and they strike out words that you really don't care about, that people shouldn't be searching for. Like you shouldn't be searching for the word the or the word are or in. These are called stop words. You remove these. So then that which remains, let us circle what remains in the meadow today, full moon night. And I'm just writing it as words, though in reality you index more than words, sometimes phrases. For example, full moon night may be worth indexing as a phrase, but we'll just keep it simple for our thing. You create what is called an inverted index, which is roughly a hash table in which the keys are the words. So for example, the word we encounter cow, and we say it was in D1, and the word moon also in D1. And then we go to the next line, the next document, and we say cows, it's in D2. So we put it here and we see the word happily. It is in D2. And so by now you must be getting a sense of what we are doing. Grazing, D2, and meadow, D2. And then we go to D3, we get today, D3, full moon, full, and let's say D3. Then moon is already there, so it is D3, and then meadow, and so D3. And so we create what is called a key followed by a list of documents that contain it. It's a simplified way. We haven't brought in BM25 or TF-ID, and let's skip it. So if a user comes and searches for happy cow, where can you find happy cow? You can find happy cow by looking at these 2 documents contain cow, and this one contains happy, or happily can be lemmatized to happy or simplified to happy. So you would say that the most relevant document would be D2, perhaps followed by D1, isn't it? The search results would be this in that order. And you can see why, quite literally, right? D2 is the most pertinent when we are talking about happy cows. Now, so this is traditional keyword search. What are its strengths and weaknesses? The strength is, first, observe that, at least in this simplified way, inverted, the search is very quick. They are order 1 lookups, right? Now, Reality is a little bit more complicated because you have to keep the importance of the term in the document and so forth, but let's keep it like that. It's rapid and fast. Broadly speaking, keyword search was based on this. And it has been the workhorse of the industry for quite some time. It has been evolving. What are its limitations? Limitations are that you need to have a match with the word or any one of its variants. And it is very sort of a non-intelligent. It doesn't understand the context. Another limitation, which I'll make sort of a straw man argument or exaggerate it, though modern search engines try to do a better job of it, is this. The language has homonyms. These are words that have multiple meanings. So if you were to open a dictionary and look for the word bank, you would see at least 3 meanings. It could be a river bank, it could be a financial institution, or it could be the act of banking. The aeroplane banked to the left in order to align with the runway for landing, right? So therefore, the word bank has 3 different meanings listed there. When a user searches for the word bank, it would be perhaps unclear which of the documents to retrieve, isn't it? And therein is the limitation of keyword search. So with this as a backdrop, on the scene arrived a very powerful approach, which is that of AI search. These are based on neural networks. These are neural architectures. In particular, they are transformers, a particular neural architecture called transformers. We need not go into it. Just consider that there are these big neural systems that are given a task. And I'll explain what tasks they are given. The task they're given is, if you're given documents, let's say document D1, and by the way, in the field of NLP, one of the most confusing things is, what is the definition of document, or what's the definition of a sentence? And the answer to that is, a document or a sentence is whatever you mean it to be, right? A sentence could be a word, it could be a phrase, it could be a genuine grammatical sentence with a punctuation at the end of it. It could be a paragraph of text, it could be a page of text, it could be a whole document, right? Likewise, when people use the word document, they could mean anything they mean by sentence. So there's a very loose association to grammatical meanings of this word. So don't take it too literally. Take it as a text. A more appropriate wording would be to say these are texts. So let us say that there is a text here, and the text is about the same text. Why not use the same text? We have these texts, and actually let me take some extreme text. We say the happy cow was grazing in the meadow. The second thing we can take, sentence, and I'll just change it to from D to S, sentence, because it's common in this form to use this, or text. The cow jumped over the moon, and S3, let us say the car needs new tires. You can clearly see that S1 and S2 are somewhat related, but S3 seems quite irrelevant, right, to a discussion about cows. So what you do is, and this is the magic that machines are able to do, they have a capacity called language understanding. Language understanding. That is why they are called language models. Large language model. Large is sort of a relative term. What is large yesterday may not be large today. But the core word is language model. A language model, you hope, captures understanding of the language, so that if a machine can understand human language, then it can do things like translation, it can answer a question, and so on and so forth. It can do all sorts of things, continuations and so forth. So language understanding machines, these are all neural nets. In particular, they are transformers, a particular architecture called transformers. And these days, people often call them LLM, though the term is gotten reserved for generative models. So I wouldn't be using that. I will just say, in particular, I'll stay away from that. So imagine a machine somehow understands human language. So how do you train such a machine? One such machine is BERT. The word, we won't go into what this means, etc. And what you do is you play with it a game. You take a text, a piece of text. For example, you can say, let us say that you take, we are done with cows, let's take something else. The young entrepreneur wants to open an ice cream shop on the beach for kids. Right? What you would do is you would go mask a word. Let's say you would hide this. You would give the rest of the sentence as input to that input sentence, and you would ask the machine, what was the word that we masked? And you keep playing this game over and over again using every single coherent text that you can find on the internet. You'll take every sentence from Wikipedia, every sentence from available textbooks that are open sourced, from novels, from whatever it is. And you keep on hiding words here and there, and you keep asking the machine. This method is called mass language model. So there's a technical term. So I'll try to explain all of this without the jargon. But I'll just occasionally mention the little bit of the jargon for reference, just to pinpoint it. But you can ignore that. You keep asking the machine, fill in the blank. What was the word that I hid? And the machine has to guess the word. And if it doesn't guess the word, there is a way for machine to gradually learn. You tell it that, you gave the word, let's say that the young entrepreneur wants to, and it comes up with the word hammer. Well, and it thinks that the word open is very low probability. It's not very likely. Okay? So then you remind the machine that no, the word was open. And the machine says, aha, is that so? Let me do something. It goes into its belly, and there are lots of knobs that are sitting there. And it recalibrates all the knobs sitting in the box. Right? Imagine that you're trying to tune into a radio station. It sort of recalibrates its knobs. And then it says, next time, I think for this, I can do better. Those knobs in the jargon of machine learning, of AI, are called parameters of the model. So, but think of them very physically as dials or knobs. Once it has gone through a lot of recalibration across every possible text that you can lay your hands on which you play this fill in the blanks game with it, the machine begins to do well. It begins to guess the word that you have masked or hidden away, blanked out. So think back, and how in the world can a machine do that? The machine can only, irrespective of how it does that, it's a separate question. But if you treat it as a black box and you're told that some alien has come from a planet, different planet, and whenever you give it a fill in the blank, the alien is always able to fill it with the right word, most of the time. What can you conclude about that alien? Your basic understanding would be the alien knows your language, understands your language. Otherwise, there is no other way that it could have filled in the blanks. Right? So in other words, understanding of language is the necessary condition to succeed in the fill in the blanks game. That is why these machines are called language understanding models. Now, suppose you have this model. This is how BERT was trained. One of the amazing things that you could do with BERT, once you do that, is that you realize that if I get a question right after BERT came out, the original transformer came out in December 2017. BERT came out shortly after, a few months later. And the moment it came out, the major search engines realized that they were looking at a revolution. Because when a user query comes, user query, let's call it Q, comes, what you could do is you could take BERT, and BERT actually, you could take BERT with a query, user query, and take a document that you have in your corpus, document that you have stored, let me call it DI, and ask it a question. How similar are they? Or how relevant is this document to the user query? Or similar or relevant? So it will produce a number between 0 and 1, relevant score. And the moment it does that, you realize that you're looking at everything that you need to create a high-powered search engine, because you can go with the query and pair it up with every single document, D1, to do let's say 10 million, right? And figure out and rank, come up with relevant scores, and then pick the top K results. That would be your search results. Does that make sense, guys? Do you see how intuitive it is? If you could make a machine produce and tell you how similar or relevant is the document to the query with a relevant score, that is it. Now you need to compare it to every other document and sort it, pick the top K. This is actually something that the search engine giants began to do in 2018 or prior to that. They realized that it produces so much superior answers that it is definitely worth adopting. And the quality of answers is amazing. And as you know, search engine are one of the greatest achievements of engineering. A lot goes into this, web scale search engines like Google or Bing, or et cetera, et cetera. A lot of engineering goes into before something like that comes about, especially when they deal with traffic at massive scale. Now, while you can do that, there was a problem. There were two core problems with this machine. So advantage is it produces really amazing results, right? Because you are understanding, the answer is derived from understanding the language. It is human-like. It's like a machine is reading the whole document and saying that, yes, it is relevant to the query. You know, you can't beat that. That's what we would do. So that's the advantage. So I will write the advantage down based on search results based on real understanding of language or context of the query, isn't it? Disadvantage, though, there were two fatal disadvantages. What were the disadvantages of this machine? Oh, there were practical disadvantages. One was the order n problem. Suppose you have n documents, cost of every query, right? Because a query, every query has to be compared with, you need to find the score. And DI belongs to a set of D documents, right? The cardinality of this is n. Number of documents is n. So that, now contrast that with naive search or the keyword search. Keyword search is in a very naive, in a very simplified picture, look up in a hash table. Now, if you remember, look up in a hash table is very simple. Now, for those of you who don't know what a hash table is, think of it as a locker room. When you go to the gym or to the airport or train station, you often find locker, post office locker. What do you need? If you have the key, you immediately walk over to your locker and you can take it out. You don't have to search for your locker. There is a way to directly access your locker and then get whatever you want. It's a simplified. It is about as rapid as can be. In computer science jargon, you say that those lookups are order one. In other words, reality is a little bit more complex, but let's say that it's in the range of order one. It is not as bad. Maybe it is log n still reasonable, but not as bad as order n, which is a linear scan, which means that the cost of every single query is proportional to the size of your corpus. So it's not practically feasible if you have a vast number of documents, right? That was one disadvantage. The other disadvantage is not only is it order n computation, you have to compare it with every document. These computes, this is a whole neural architecture, neural net. Neural nets, what they do is they actually do a lot inside them. There's a lot of matrix, big matrix multiplications. And then there are these things called activation functions, right? Suffice is to say that they do vast amount of computations in their belly before they produce a result. So what it means is that even any particular comparison operation to produce a score, this process itself is expensive. So now we have a double whammy. Every single comparison is very, very heavy, and you have to do n comparisons, right? So that obviously makes it not a very practical solution if you have sufficiently large number of documents to search from. Are we making sense, guys? Right? I hope. And those of you who have a semi-technical background, I hope you can let me know if for any reason you feel you're not getting it. Do interrupt me, please. Huh? So this is your problem. Now the question is, how can we have the disadvantages? How can we get rid of the disadvantages without getting rid of the advantage? Go ahead.
Big question. So just like that was O1, what's the algorithmic complexity? Is this polynomial?
Inside the
for calculating the score, it's Q.
No, it has nothing to do with the number of documents. Because it's one query compared to one document will have a finite cost, which is proportional to, roughly speaking, how many parameters you have in the model, because these are matrix.
Roughly, is it ON?
N being what? N being the number of
documents?
No, it has nothing to do. See, each of them is order one, but you have to do, for every query, you have to do n times.
So that should be ON.
Order n, except that it is order n. The question is, what is the prefix to the order n? Okay. Right? What is the cost of each compute? The cost of each compute for a neural search, this is prohibitively high. You can't scale it. That's the problem. So again, so we have framed the problem now, right? The framing of the problem is, we see a lot of advantages in using a language understanding machine, something like BERT. But we don't want to pay the price. The price is ridiculously high, right? It's not feasible practically. So then comes yet another idea, which says that we will teach the machine, the training the machine is done using something called a loss function. We will skip that terminology, but look at what it means. What it says is, take a page. So I'll just do it in 2 dimensions, right? Take a page. Now, if I put all your so what happens is these machines, they produce a vector. A vector. Vectors are nothing but points. They're fancy words for points in a Cartesian plane or higher dimensional Cartesian plane, right? So it could be, let's say, 1,000. But here, for sake of simplicity, we'll consider r squared. So whenever somebody says vector, think of it as just points in a Cartesian space, x, y, and many axes space. That's all they are. So the documents are gone. Let's say lots and lots of documents are there, and they have sat here. Now you tell the machine that, see, you need to place the documents in this space, in this page, in such a way that if two documents, A and B, or two sentences synonymously, land close to each other in this space, right, then that should happen only if their meanings are similar. Right? On the other hand, a document that is irrelevant, see, should be here. Right? Far off should be, irrelevant document should be not near this. Now let's go back and revise what documents we gave. We said S1 is the happy cow was grazing in the meadow. S2 was the cow jumped over the moon. And the third sentence was the car needs new tires. So what we are saying, the S1 and S2, which are both talking about cars, it's about cows, they should be proximal to each other on the page, on the Cartesian coordinates. But this one, talking about cars, should be far away. Now the question is, the machine is given lots of these, what are called triplets. Given a text, give it a similar text, and give it a far text, a random text. Right? So TS random. And you say, play this game. Go embed it, go put it, create vectors out of it, or rather points in this page out of it. But make sure that T and S are close, but R is far away. And it has to keep doing it with millions and millions of such examples. Right? And the amazing thing is, these machines, these neural architectures, I suppose in the beginning they scratch their head and get it all wrong. But after a little while, little tiny step by tiny step, they begin to get the hang of it. And they succeed at doing it. The wonderful thing is they actually succeed at doing it. It's almost miraculous that they can do it. Okay. This space is called semantic space. Semantic embedding is the only jargon that I would like to put here. Semantic embedding. Why? Embedding just means vector, point. Embedding, think of it as a point in a space. Right? So for example, when you hide a toy in your bed, we know exactly where the toy is, at some location on the bed. In the same way, you can think of a Cartesian plane, in this case a plane, and where you put the point is sort of embedding it there on the point. Imagine it as a pin that you embed on the page. Right? That's what these points are. But do you realize that a machine that succeeds at doing it will end up creating a space and a set of embeddings or vectors which understands language and then does it, right? It has to know what is it that these sentences are talking about. Then only can it put it proximal to other sentences that talk about the same thing, right? This was a fairly important paper. This work came out pretty soon after BERT. It was called the sentence BERT. It was the first paper. And after that, this technology is called text encoding or text encoders. And it has been quite a race, quite a fun thing. There's a leaderboard called the MTEB leaderboard. Hugging Face maintains it, an organization called Hugging Face maintains such a leaderboard. And what happens in the leaderboard is every person who thinks they have a smarter way to create a semantic embedding creates a model that understands the language, the text even better, and then shows the benchmark and says, see how well my model is doing. And then they get a place under the sun. They're ranked somewhere on the leaderboard. And it has been quite a race, actually. Just when you think no more innovations can be done in creating a better semantic embedding, comes yet another paper that beats everybody. Right? So it has been a fairly rapid evolution and a fun evolution to see how much nicer and nicer text encoders you can create. Now, there are text encoders which are just for English, general purpose English. There are text encoders which are domain specific. You can say, okay, I want it to work really well for finance, because in finance, the word bull and bear mean entirely different thing than in general English, than in general English. Right? So then you can do domain adaptations. You can have models specific to a domain. You can have models that do only one language. You can have models that are multilingual, and then there can be degrees of multilinguality. You could have multilinguality across 5 languages, 10 languages, only the Latin languages, including other. And nowadays we have text encoders that use the phrase "no language left behind." Right? They span close to 200 languages. So it has been a wonderful, wonderful evolutionary journey for people to create these embeddings, these semantic embeddings. Why would people take it so seriously? Why would the research crowd have so much fun doing this? There's a reason for it. Because it turns out that if you can create a good semantic embedding, you're looking at a solution to do search in which you can have the advantages we talked about without the disadvantages. What do we mean by that? Let's say that you take your documents D1 all the way to D10 million. For each document, you produce a vector. Like you figure out what the point is in the embedding space. It's a one-time cost. You find a new document, you can pass it to the machine, and you make it into a vector, and you're done. Then what you do is you put it into what is called a vector database, which simply means a way to store vector. Now, the most naive storage of vector would be just as an array, right? You can say E1, and you can remember that E1 came from document 1, E2, E10 million, let's say. Right? And you keep remembering that this is D2. You have a dotted line somewhere, remembering, not in the vector database, somewhere you remember the reference that this vector came from this. Are we together? Now what you do is a user query comes. User says, let's say the user says something about, what are we talking about here? Cars, needs new tire, right? You say that, how do I replace the tires on my car? User has sent this query. This is your query. Now, what can we do with this query? What we can do is we can convert the query, pass the query through the same machine, which is again an order 1 operation at runtime, order 1. You can pass it to the machine and you would get a query vector. Or simply put, without using fancy jargon, you would end up with that query will land somewhere. The query will land, let's say, somewhere here, the red dot, right? This is your, because ultimately vectors are nothing but points. So far? Now tell me, what are good search results? Would you agree that all the documents around it, like the vectors around it, represent documents that are talking about cars and tires. It's plausible to believe that, isn't it? And in fact, it is so. So you go and pick the k nearest neighbors, then to the vector find k nearest neighbors, right? You find k nearest neighbors, and then those documents become your search result, right? So now you may say that, okay, now wait a minute. How did it solve the problem? Because for me to find the k nearest neighbor to this point, I still have to stare at all the points and find the points, the query points distance to each of the other points. That problem still remains, right? It looks as though it is a top k nearest neighbor remains a order n problem, right? And the other so that is a problem. Let's hold on to that. Actually, let's address that first. It turns out that top k nearest neighbors, in practice, you never do exact search. There are methods which are called approximate k and n, approximate k and n. They're usually called a and n methods, approximate nearest neighbor methods, which can actually find the top k in no worse than log n steps. So that's a huge simplification. Actually, they are even more efficient. You can do it. I'm just giving sort of a worst case thing. And I'll give you you say, how in the world can you do that? So here is a simple intuition. Suppose you have pre-divided the space into regions, right? You have successively decomposed this. There are algorithms like, I won't go into the technical, these are called KD tree. If any one of you are familiar with it, it is, but ignore that. It decomposes the entire space in a very judicious way into subregions hierarchically. So suppose this point lands in this box. You would agree that I need to find neighbors only in this box. Now, if this point was on the border, then searching within the box would be not exactly right. I'm missing out points which may be in the adjacent region. And there are ways to adjust for that. But in any case, a region and its couple of adjacent regions should be enough to find the nearest neighbors. You don't have to search the entire space, isn't it? So therefore, you can reduce the problem drastically from an order n problem to a smaller problem, faster problem. The reality is today there are absolutely battle-tested, massively scalable and high performance implementations of nearest neighbor search. One of them, which is very popular, is which is called FAISS. It is released by Meta. Could you guess the acronym? Semantic search, exactly. Right. So it actually gives you very, very rapid and fast, and sort of a workhorse of the industry. Open source, you can download it. A very, very wonderful piece of software. So it does that. So now the order n problem is gone. But we have another problem to deal with, which is that you still have to compute the distances. It turns out that to compute the distance, which you do by looking at the angle, 2 points which are near each other will have a very tiny angle between them. Right? See, when we look up at the sky and we say this, look near that star, what we really mean is that that star is not near. In real life, that star may be very, very far away from this star, but the angular distance between them is small. It appears as though this star is the neighbor of that star, right? So for example, you may say Cirrus. To find where Cirrus is, we may recognize the belt of Orion and then say, okay, if you're looking at that now, look left, go left, and then look down from it, and so forth. So we always use angles to it. So it turns out that in higher dimensional spaces, that's the technique you use. So when you compute the angle between cosine theta, similarity between two vectors, 2 points, it is a very cheap operation. It is very cheap computationally. It is, dot products are the workhorse of mathematics and machine learning in particular. Libraries to optimize it have been, it's very, very fast, let's just say. So what it means is that not only we are doing it in less than order n operation, each comparison of a query against a document, you're not comparing this. You're instead comparing query becomes a vector, document becomes a vector, which has already become a vector, D, and you're comparing these two, isn't it? And that also, not all the documents, but you already know in a small region, you're doing it. I can give you that intuition if that intuition is a little hard to get geometrically. Here is something. In schools, we have children, they are bucketized into discrete buckets. These are usually called grades. K, kindergarten, grade 1, grade 2, grade 3, all the way to grade 12. Now, think about it this way. If I told you I'm looking for people who are 6 foot 3 inches, would it be sensible to search across the whole school, or would you just look into the high school? Isn't it? You might miss an extraordinarily tall person in middle school, but getting to high school should be enough. So that shows you that if you pre-bucketize data, then you can find nearest neighbors quite easily, right? That's sort of the intuition. So at the end of it, what happens is, let's go back and look at the disadvantages. The advantages remain. It's a semantic embedding. The disadvantage, this disadvantage goes away. It's not order n. And not only that, this is inexpensive. It's a cheap compute. Instead of firing up an entire neural network to compare a query against a document, you are just doing a dot product between two vectors, cheap compute. And thus is born, with these things, is born what we today call semantic search. So the semantic search. So what are the key ingredients of this semantic search? What we do is, the steps are, first, indexing. Take every text, I'll just use the word text rather than sentence or document, and create, number one, create a vector embedding, namely a point in the Cartesian space. Number two, give it to a vector DB. Actually, these days, vector databases are pretty smart. You give it an encoder. So what will do it? Encoder. This is a neural network. Remember that magic box we talked about? Language understanding box, text encoder. Text encoder will do it. And then you give it to a vector database and say, store it. So now it will have 10 million points stored. Next, what you do at inference time, at runtime, users are coming with their queries. A query comes, you pass it through the same encoder, you get a vector, you go to the vector DB, and what comes out? Top K neighbors. But you know that if they are top K neighbors in the semantic space, then they are actually the perfect candidates to be the search results, right? So another name for this would be search results. And if you think about it, we think of search engines to be this, a magic box in which we give a query and out comes search results, isn't it? Right? Therefore, we are looking at a search engine. Now, I'll pause here and I'll take a couple of questions from anybody.
The score, calculation score, which is like what to display first, will be based on the angle distance. That's
Cosine is one, dot product also. There are many metrics, there are many ways of comparing distance. The ways that don't work in high dimensions are Euclidean distance, because in high dimensions what happens is all the points fly away from each other. But yes, cosine is one of the most, it is perhaps the most popular similarity measure. Distance is the converse of it. So yeah, somebody on Zoom had a question.
So this will probably come a little later, but the encoder that we use to convert to vectors, it has to be the same encoder or connected to the LLM that we are going to use later.
No. LLM is completely different. Ignore that. The point is, whatever encoder you use to create the document embeddings, you need to use the same encoder for the query also, because every encoder has its own way of thinking. So you can't mix and match. You can't say that, hey, I got embeddings using encoder this, but tomorrow a better encoder has come out. So I can use the better encoder for query, because then it won't make sense. Yeah.
Okay.
So you have to be consistent. Keep an encoder for both your documents and the user queries. Yeah. You can't mix, you can't change that.
Okay, thanks.
One question, another clarification.
Wait, let me make sure we are done with it. Sanjeev, anything else?
No, that's all. That's all. Thanks.
Go ahead.
So when we say that we store a point in the Cartesian space,
yes,
but then also use a term that is a vector embedding.
It's a vector because a point,
right.
the coordinates of a point are a vector.
Okay, so the value is basically a vector.
Exactly. So it will be an array of numbers, right? Along this axis, along that axis, along that axis.
The value that is stored is
an array,
basically a tensor, or just
in this particular case, just a vector.
Okay. For teaching, it's a vector.
Yeah.
But it can be a tensor.
A tensor, it's a one-dimensional tensor.
It's a one-dimensional. Okay.
Yeah. Remember, tensor is a generalization of a vector and a matrix.
Okay. So it's is it a scalar value? Is it
No, it's not a scalar value. Scalar value will be like today's temperature.
Sure.
This is a vector. Remember, even in XY in a plane, to represent a point, you need its X and Y coordinates.
So in the Cartesian coordinate, which is the point, the value stored is the vector.
Is the vector, exactly. Go ahead.
So while explaining sometime back, he said you tell the computer or the process to place similar meaning sentences together, right?
Yes.
How does he understand that?
For the sake of this course, see, the technical answer is, and I don't want to go into that because you are in the course where you learn this properly, but it is a loss function. You use what is called a contrastive loss. I did put the word on the table. Yeah, it uses something called contrastive loss. Literally this, you see this triplet that I talked about? You basically say that, see, you need to learn to put similar things together and dissimilar things far from each other. To do that, I mean, what I just said in plain English, if you say it in mathematics, it becomes a specific loss function. Okay, that's it. That's all it is. Any other questions, guys?
Yes, that is the key. Right?
That is the key. That semantic embedding is the key. And semantic embedding, therefore, allows for semantic search, which is also called AI search or dense search. So let's write down the synonyms that it has. AI search, dense search, etc. Vector search and so forth. People use this quite a bit. Now, the question that arises is AI search always superior to the old style keyword search? And I don't know if I'll get time. Maybe tomorrow we'll show you a comparison. Mostly it's true. If the query that you give is descriptive enough, it has enough meaning in it, then the machine will understand what you're talking about. And it will give it to you. But if you just give a word bank or something like that, the machine would say, I don't know. Then it's hard to say that it will beat keyword search. Keyword search may do better. Right? That is one aspect to it. Now I'll bring a topic called something more fun that you can do with vectors. Because you have language understanding machines, language understanding models, or just language models, right? That are acting upon your text and producing the vectors. Here's an interesting thought. A document or sentence went in, or text went in, it became a vector. But see, language is a form of communication. And we communicate, like for example, I'm not communicating with you as much with the written word, written text, as with just speech. I'm talking to you. That is audio. And that conveys information as robustly as text does. Right? So what is a language? Language is a means of communication. It could be audio. It could be text. In fact, for the longest time, a text as a form of communication is a very recent phenomenon. Throughout history, most of humanity had an oral tradition. You could communicate using pictures, right? As they say, a picture is worth 1,000 words, right? You can show something, and enough, that itself conveys a lot. You could show a video, right? And there are many ways of communication, sign language, and it goes, there's more to language. For example, your gestures or the tone of your voice says a lot sometimes, right? So, as you know from experience, so can a model understand at least some of it? It turns out that we have models now. These are called multimodal models that have been extended to understand images, videos, audio, and sign language, and even data, heat data, thermal data, depth data, and what is important in is 3D geometry, the normal to the faces. Like, if I know the normal, if I give a face, the picture, but I can tell you what the perpendicular is at any given point, you can essentially infer the 3D geometry of the face. So all of these things are languages to express, to communicate. Can we have language models that can understand all of this? We have. It has been one of the great achievements of the last few years has been that now language models understand, these are multimodal language models, understand all of these modalities. You say that these are different modalities, text, picture, etc., etc. And in the second half, all of these things that I explained will become rather real when I show it to you in action. Okay? So that brings up very interesting question. Can I ask my question in text, but not only get text as answer? If I can embed images, videos, everything as vector, the vector space doesn't care what the vector came from, right? All it will do is it will tell you the nearest neighbors. So those neighbors could be text, they could be pictures, they could be audio, they could be video, and so forth. So can we get results of all of those in our search results? And one of the great achievements of the last few years is you literally are, with AI, you are doing semantic search. You realize that this was simply not possible in the traditional way of searching, which was limited to the world of text. Right? Because keywords are words, they're text. But you can do with images. So your query could be a text, and out will come search results, which are words, which are text, which are images, videos, audio. Alternatively, you can have image as query and text can be a search result. For example, you can show it a dog and it might come up with some great comments about dogs. Pictures, text about dogs, or poems about dogs, or whatnot, right? Or show you a video about dogs. Isn't that wonderful? That you can mix, the query can be in any of the modalities. It can be in text, it can be in image, it can be in video, it can be in audio, and so forth. And output, and it could be in any language. Because it doesn't matter whether you speak in English, or you speak in Mandarin, or you speak in Tamil. Despite the divergence of these languages, if the machine understands what the language, what the text means, it will of course create a vector that is specific to its understanding of the text, not the language in which the text is written, isn't it? So therefore, you can do multilingual search. I'm reminded of a wonderful project that one of the participants in our RAG bootcamp did a couple of years ago. There's a part of India, South India, called Tamil Nadu. In that region of India, there's a language called Tamil. It's a rich language with a vast history. They have a form of poetry or sayings, aphorisms. Those are called Tirukural. So for every situation in life, it has something to say. Right? You just had a quarrel with your friend. How exactly, what's the wise way of handling it? There is some advice there. Right? So Tirukurals are things that people from that community absolutely swear by. Anybody would like to vouch for the Tirukurals here? You agree? That's right.
Absolutely.
Absolutely. So what our participant did is, and he'll be giving one of the subsequent talks. Actually, 2 weeks later, he'll be doing this weekly paper reading. He created an interface in which you could ask a question in English. It would dip into the Tirukural, find the most appropriate advice for you from the Tirukural, which is written in Tamil, and then it will understand what it is saying, and then rephrase it, not just translate it, but rephrase that advice and similar advice into what is appropriate for your situation. Right? And he apparently hosted it. From what I understand, it got so much traffic because it was a free thing, he had to take it down. But it became really popular. Right? So that speaks to how useful AI search engine can be. Right?
As if just when I was I left I had to go from the LLM1, but in the first assignment of the LLM1, I remember you talked about this. So the assignment we did or picked up was doing the same thing. It was a haiku. So essentially, you pose a question, and it would bring up the one of the haikus out of that it had. It would rag from a big text of koans, actually.
Right.
Not haiku, but koans.
Wonderful.
Yeah.
Yes, I remember your demonstration. Yet another great example of using AI search and RAG and LLM also along with it. So guys, today I want to limit to the topic of AI search and multimodal search. What I would like to do is, it's 8:20. Let's take a 20-minute break. Is that fair? And then let's do a lab on this. So in the first half of the session, we covered semantic search. Now, we did mention that semantic search has the power to do things that traditional search cannot do so well. Not only does it, in many situations, give better search results, but also it opens the door to multilingual search, multimodal search, and all of that is groundbreaking. Right? So let us see it in action and see if it is really true. I brought some examples. This lab notebook, first I will take you through that. And those of you who are interested in knowing how to set it up on your machine so that you too can reproduce this on your laptop, I will walk you guys through that session too. So just to recap, what we do for a document, just writing it in mathematical jargon, we convert it to a vector, etc. But I'll skip that. We have been through all of that. I'll let you read this. In terms of code, it's extraordinarily easy to use semantic search. In this particular example, you choose, remember I said there are competing models in the leaderboard to do encoding of your text. Here, we are not taking the best of the model, but we are taking a model that is good enough because we want it to be achievable on your laptop, that it should actually run on your laptop, even if you don't have a GPU. So let's read through this code. What is it trying to do? And this is only for people who are technical. If you are not, you can just wait for me to move ahead. This is it. You take a model and you create an embedder that will create embeddings of the model. Then you go, we will load a small corpus of documents. So here is the corpus of those documents. I created a corpus of some maybe 15 odd documents. These are some of my favorites or something. One of them is Through the Looking Glass by Lewis Carroll, is the Jabberwocky. This text has a unique quality to it. Not a word makes sense. Not a sentence makes sense. But if you sort of say it aloud, it all seems to make sense. It was brillig in the slithy toes, did gyre and gimble in the wave, and so forth. Right? So interesting. Then I have another quote from Charles Dickens, Tale of Two Cities, which is, it was the best of times, it was the worst of times. A very popular passage from Dickens. That's how his book opens. And another passage from Dickens, and another passage from Dickens, which is towards the end. Then there's a passage from Mark Twain about dogs, where he says a dog is a gentleman, and I hope to go to his heaven, not man's. Right? Then there's Tweedledee and Tweedledum. Then there are some phrases about golden retrievers. Then a Keats poem. Then Attention is All You Need, a technical paper. Another text on back propagation, a technical topic. Something from Wordsworth, Lucy's poem. Something from Davis' poem, and so forth. So in other words, I created a collection of text which had some degree of variety to it. Now what I will do is we will look at what this, when a machine creates a vector out of it, what does it look like? Right. It turns out that, oh, in this, we don't show the search results.
Since because this notebook is pretty large, we had to
check in without the search. Would you mind sharing your screen so I can walk through this?
I do not have the outputs.
You also don't. Would you mind running it?
Okay, yeah, give me a second.
So this is a notebook that, so I'll explain what happens here. You create an encoder, you create a small vector database, which is literally an array of vectors that you will search through. You ask for it with the text. Now the text is quite interesting. And when the results come, you'll see how utterly impressive it will be. I'm searching not for keywords, but observe what I'm searching for. Our friendship with animals. Our friendship with animals is an emotion. It's a state of mind, isn't it? So we are not looking for a thing, but an emotion. And the most amazing thing with the search results are, when it comes actually, we'll see, is that the first and the second search result will have neither the word friendship nor the word animal in it. In fact, the first text that has the word animal in it comes much later. And that's a remarkable fact because a keyword search engine wouldn't have found it. Right? That we'll see that shortly. And if you just reflect upon it, you'll realize that it is truly capturing the meaning of text and going against the meaning of text, using that to create search results. The second one is the visual search. In the visual search, we are, maybe I can run it at the end of it, guys, if needed. I will run this notebook so you can see the results if my team doesn't pull it up quickly.
I have one with results.
You have that. Would you mind sharing your screen? I'd like to walk everybody through it. So yeah, let's go to the first search results above. Yeah, let's stop here. So we search for, and thank you for helping me out, Rajesh. So see, guys, these notebooks are huge in the sense that these are AI models and their images and so forth. So we have checked in version without the results. So which is why I couldn't show that. Our friendship with animals. It comes up with some results. And if we scroll down a little bit, let's look at the first search result. It says the golden retrievers are not bred to be guard dogs. And considering the size of their hearts and their irrepressible joy and life, they are less likely to bite than to bark, less likely to bark than to lick your hand in greeting. In spite of their size, they think they are lap dogs. And in spite of being dogs, they think they are also human. And nearly every human human they meet is just to have the potential to be a boon companion who might at any moment cry, let's go, and lead them on a great adventure. So guys, when you read this sentence, the remarkable thing is there is neither the word friendship nor the word animal. This result simply couldn't have been produced by a keyword search engine. Do you see that, guys? But who could have written this sentence? It would be a person who feels a deep friendship for dogs, a deep friendship for animals. I hope you would agree with that. And so imagine what a leap forward it is when AI understands language and says, if you're looking for a friendship with animals, this passage is the most appropriate passage. Okay? That's the remarkable thing. Let's look at the second search result, which is a little bit shorter. If you're lucky, a golden, no, it's still there in the same one, result number 2, rank 1, yeah. If you're lucky, a golden retriever will come into your life, steal your heart, and change everything. Once again, guys, there is neither the word animal nor friendship here. It is in fact in the third search result that the word animal will come towards the end. If a man aspires towards a righteous life, his first act of abstinence is from injury to animals. Here, at least the word animals are there. But you would agree that each of the 3 sentences could have been represent a sentiment, and that sentiment is a friendship for animals. And it understands, the machine understands it. That is the leap forward. Now let's go to visual search. Suppose you give the machine a picture, but see a picture, this is a golden retriever image from Wikipedia. Now all golden retrievers look alike. Mine looks almost identical to this. So my first reaction was, isn't it mine? So now think about it this way. A machine does not understand pictures. All it gets is a stream of pixel values across 3 channels, red, blue, and green channel. It is just a long stream of numbers, matrix, 3-dimensional matrix of numbers and images. You give that as your search query. Nevertheless, it is able to search in text and find the nearest match. Now, because it's a toy example, we have taken a few sentences which have dogs and a few sentences that don't. And let's see what the search results say. And when you look at the search results, you notice that the very first search result says golden retrievers are like little children. From that, you can conclude that the machine has figured it out, that it's looking at a golden retriever. Isn't that amazing? Think about it. Isn't that amazing? And the other one is a smiling dog, which I found quite astounding, because you have to be a golden retriever owner to know that this golden retriever is actually smiling. So this is the power. We gave image and search text. Now we go down, we can give text as query. This type, oh no, there's some error here. Let's keep going down. And some configuration file not found. Okay. No, that's all right. We can, this has to be rerun with your laptop's values. Guys, this code will run on your machine, but we need to configure it properly. Keep going down, all the way down, and all the way down. Yeah, keep going down. Yes. So suppose you give it a query to love an animal. What we did here is we took 25,000 images from Unsplash. Unsplash is royalty-free images. And there is a database, open source database of 25,000 random images. 25,000 is large enough to contain just about everything you may imagine. Now, if you search with the phrase to love a dog, observe that it hasn't just brought pictures of dogs. If you look at these pictures, you will see people in the act of loving a dog, right? Or a feeling of love is there in these images. And that's the most remarkable thing that you can achieve with semantic search, multimodal semantic search. If you give it a query, a house near a lake, it will find this literally not just a house or a lake, but quite literally a house, a nice idyllic location on a lake, you'll find. Likewise, the next one, if you say jumping dog, it will bring up jumping dogs. Right? And you can go on in this vein, a path through a forest, and it will find the paths through the forest. Right? So you can play around, guys, as you get this code, this notebook, load it onto your laptop, run it. You need to run it, but then everything will work, and I'll help you configure it and run it. Right? Now, this is I must tell you that this Jupyter notebook is a bit large. It's going to download 25,000 images from the internet onto your machine. So beware of that. I hope you do have enough storage. Those images are very small. So the database size is not large. Nevertheless, you should be careful. So that concludes today. Go ahead.
One question. So in the case of the image search, just like we had the text encoders, I'm assuming we have image encoders which will break down and understand the context, just like how it's understanding text. Here in this case, it's understanding images, do entity detection, etc., and understand whether it's a dog and for example, emotions of the dog or the act of the dog, it's running, jumping, whatever it is, and so on.
It's pretty good at it, and we'll learn how it does that in the RAG course.
Okay.
Right? In the bootcamp, if you do that, because we have a large, good expanse of time to go deep into these topics.
Sure.
We'll go. It was one of the great breakthroughs, CLIP, and then vision transformers and CLIP, and then blip and blip 2 and so on and so forth, and lava. That's still amazing. Even though it's been a few years, it still feels amazing, right? And the pace at which these things are moving is absolutely breathtaking. So guys, today I did not go into RAG for a reason. I wanted to prepare you guys by first finishing semantic search. Today we'll consider at the end of semantic search. Tomorrow we'll do RAG, and I'll give you the architecture of RAG, and I'll show you a few simple examples. The subsequent week, Wednesday, we'll do something a little bit deeper with RAG. Right? But I hope you got some flavor of what this field is all about. Any comments, guys? Thank you, Rama.